This is Mrs. Murphy, and today we're going to go over some different numbering systems. We're going to start out with a review of decimal numbers, so it'll help us learn the different numbering systems. And then we're going to go over hexadecimal, and we're going to show you the importance of these numbering systems for data representation.
Okay, time for a little review. This is a review of numbers. We're going back to like second grade. I swear I've seen my little second grader have questions like this. The Common Core is now taken over, so it might be a little different for you guys when you were in second grade. But they used to teach you using flats and rods and units to represent the base values. A flat was 100 squares, a rod is 10 squares, and a unit is 1 square. So if you have a number, let's just say 247, that would be 2 flats, 4 rods, and 7 units. Thanks, Common Core. Well, as you get older, you realize that each digit has place values. So those flats are in the hundreds place, those rods are in the tens place, and the units are in the ones place. Okay, a little review of why they have place values. Well, it's because the numbering system we use is base 10. That means we start at the right-hand side with 10 to the power of 0. Why? Because numbers actually start at 0, not at 1. This is computer science, remember, not math. Okay, so then you have 10 to the power of 1 and 10 to the power of 2. So going back to the ones digits, what is 10 to the 0 power? Well, anything to the 0 power is just 1. 100 to the 0 power, 1. 52 to the power of 0, 1. Yep, everything to the power of 0 is 1. Okay, easier one now. 10 to the power of 1, well, that's 10. And then we have 10 squared, that's 100. So we have the ones place, the tens place, and the 100s place. So we put in our numbers in their place value, and we can write the numbers as an equation. Our number 247 is really just 2 times 100 plus 4 times 10 plus 7 times 1. So why the heck is Mrs. Murphy teaching us this way? Well, I'm kind of hoping you're going to see a pattern for the different bases of numbers, because if you can see the pattern, you won't have to memorize all the conversions. You'll just keep following the pattern every time. Okay, so here we go with binary. This is base 2. We're going to start with 2 to the power of 0 on the right-hand side. Then we have 2 to the power of 1, then 2 to the second power, 2 to the third power. Why 2, you may ask? Because it's binary, or base 2. Well, 2 to the power of 0 is, what did we say that anything to the power of 0 is? Remember that just a few minutes ago? Yes, 2 to the power of 0 is 1. Okay, then we have 1. So we start with 1, 2, 4, 8. Are you noticing a pattern yet? Okay, what number comes next if we keep following this pattern? Did you say 16? Great job! Okay, enough with the Dora the Explorer references. You would not believe the number of times I've had to sit through some of those episodes. My kids actually respond to Dora the Explorer talking to them. Anyway, on with this. This can also be written as an equation. So if we put in our binary number 1010 into each of their place values, you're going to get 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. Well, even easier, all you have to do is add all the positions that have 1s above them. So that will show you the larger number. So you got 8 plus 2, which is 10. So here we have a longer binary number. There's a total of 8 digits altogether. Of course, in computer science class, we call those bits or binary digits. Just one of those 1s or 0s is a bit of information. So now if you have a group of 8 bits, then you have a byte of information. 1 byte can store a single character on a computer. That's it. So the reason we're translating a binary number that's 8 bits long is because that's how information is stored on a computer. So here I have that same number again, that same binary number, but I've put it into the chart so we can see it with its place values up at the top. I've extended out the numbers for an 8-bit binary number. Now if we look at the numbers in the top column, they start at 1 and they double each time as they go to the left. Remember that 1 stands for 2 to the power of 0. Anything to the power of 0 is 1. And that 2 stands for 2 to the power of 1, and so on. But sometimes it's just easier to see that the numbers double each time. So you start with 1, and then 1 doubled is 2, and then 2 doubled is 4, and then 4 doubled is 8, and 8, 16, and 32, and 64, and 128. Well, remember with our decimal numbers, just the regular numbering system that we use, in English, and not computer, the 100s place was on the left, and the ones place was on the right. And this is the same with binary numbers. The smallest values on the right-hand side, and the numbers get larger as they go to the left. Now, we have our binary number positioned with each digit in its correct place value. All you have to do is find the ones in the binary number and add up all the numbers up at the top. So we have a 1 under the 128, and a 32, and a 16, and a 2, and a 1. Well, then that means all you have to do is add 128 plus 32 plus 16 plus 2 plus 1, and that will give you 179. Okay, here's one for you to try. See if you can do it all on your own. I'm going to show you in 30 seconds. So did you get the answer 91? We got 101111 is 91. You notice you can leave out the preceding zeros off of the binary number. You know, if you ever say like 91, you don't ever say 0 100ths and 91. We just say 91, as is the case with the zeros before the first one on the left-hand side. Don't do it with the zeros on the right-hand side. That would mess up your entire number. But if you have any zeros on the left-hand side of the number, you can kind of drop them if you want to. Okay, now we're going to go the other direction. We have 37, and we want to convert it to a binary number. So we put in our numbers 1, 2, 4, 8, 16, all the way to 128. This is our byte of information, if you remember. Okay, so here is the rule. You're going to place a 0 if the number that we have is smaller than the place value. And you're going to put a 1 if the number is larger or equal. Okay, let's kind of show you how this plays out. Compare the number 37 to the first place value of 128. Okay, it's smaller. All we have to do is put a 0. Check the next number. Next number, 64. 37 is still smaller than 64, so put a 0. Now check 32, larger. Okay, we got to put a 1, and we're going to subtract out 32 from our number, and we're left with 5. So now we're going to be comparing 5 to the next place value. The 16, it's smaller, so we're going to put a 0. We're going to check 8. 5 against 8 is 5 is still smaller, so we're going to put a 0. Okay, 5 is larger than 4, so we're going to put a 1 on the left with 1 left over. So now all we have to do is compare the 2. Well, 1 compared with 2, we're going to put a 0 because 1 is smaller than 2. And 1 compared with 1, since they're both the same, we're going to put a 1. If you ever left with a number larger than 1 on the last place value, that means you kind of did something wrong. So we're left with 1, we're just going to put a 1, and that is our binary number, 00100101. Okay, your turn. Convert the number 29. So 29 is less than 128, and 64, and 32. Zeros, all of them. 29 is larger than 16, so we're going to put a 1 and subtract out the 16. We're left with 13. Okay, so 13 is the number we're comparing from here on out. 13 is larger than 8, so put a 1 there, and we're going to subtract out the 8, and we're left with 5 as our comparing number. 5 is larger than 4, so we're going to put a 1, and we're left with 1. 1 is smaller than 2, so you put a 0, and 1 in the last position is the same, so we're going to put a 1, and that's our binary number. So 00011101. So binary numbers are a literal representation of how data is stored on a computer. Us humans interacting with computers can't really understand all those ones and zeros as fast as a computer can. For example, just looking at this binary number, can you tell that it's the answer to life, the universe, and everything? Oops, sorry, nerdy reference. Let me try that again. Just looking at this number, can you tell that it has the value 42? No, we have to calculate it. We're human. Okay, so it's difficult to use decimal numbers on the computer because it's a binary numbering system. The two numbering systems don't line up very well. So this is why many times hexadecimal is used, or base 16. Okay, so this is a base 16 numbering system. We're going to run out of digits using our base 10 numbers. But that's okay, we'll just start using letters. We'll show you how. Okay, we're just going to count for right now. We're going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, out of numbers. Here comes the letters. 10, see that's A. A is 10. And 11, that's B. 12, 13, 14, 15. Okay, F, that's the last digit. It kind of acts like the number 9 in decimal because it's the last position and all. So that's the last one before going over to the next position. Just like in decimal, we put a 1 in the 16th position. It's not the tens position, it's called the 16s position in this numbering system. So this makes 16 look like the number 10, but since it's base 16, it has this 1 0 has the value of 16 and not 10. Okay, so now we have 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Then we'd have to do it all over again, but I really didn't want to do this many animations in PowerPoint anyway. This is already like, what, 62 animations? So I'm just going to stop here. But what would happen is the 1 in the 16th position would change to a 2, and the pattern would start all over again. And then you'd have a 3 and the 4 all the way to F, and it would just kind of continue on in the same pattern. So here we have the number 5C in hex. We're going to find out what this number is in decimal. But we're going to use the same pattern and equation we had with the binary and decimal numbers. Well, base 16 is just 16 to the power of 0 in the first position, which is 1. Then we have 16 to the power of 1, which is 16. So if we wanted to write out the equation, it would be 5 times 16 plus C. Well, 5 times 16 is 80, and C is just 12. So you're going to get 80 plus 12 is the number 92. So 5C is 92. Okay, your turn. Here's the hex number 2B. Try converting that to decimal. All right, did you get that? We got 2 times 16 plus B, or 2 times 16 is 32, and B is 11. So 32 plus 11 is 43. So 2B in decimal is 43.
Okay, now we're going to go the other way around. We're going to convert decimal numbers to hex. We have the number 58 that we're going to convert to hex. So to find the number, you divide. But it's not the division you do on your calculator. We're talking about the division you did like in second grade. You remember that? You said what the remainder is instead of calculating the decimal places. So 58 divided by 16 is 3 with a remainder of 10. So 3 goes in the 16's place and 10 goes in the 1's place. Only since it's hex, we don't call that 10, we call it A. So the answer is going to be 3A.
Remember when we did those web pages, when we added some color to them? Those are just hex numbers in your web page. It's called an RGB color code, since there's 3 colors represented in one hex number. The first 2 digits of the hex number represent red. The next 2 represent green, and the last 2 are blue. So in this case, the red would be a very high number, and the green and blue are 0, so the color FF0000 would be red. If we had 0000FF, that's 2 F's in the blue's position, blue would have the highest number, so that color would be blue. You can have any combination of colors to give you the exact color you want. All F's are white and all zeros are black, but you have any color in between. And that's where these hex numbers are coming from, and that's kind of how they work. Okay, so the next numbering system I want to show you is oct, or base 8. I'm not going to require it for the test. You're not going to see it on anything. I just want to show you that the pattern still works. Plus, then you'll get the joke of the day on the last slide. So I have the number 1, 2, 3. It's not 123, remember, because this is the oct numbering system. So it's 1, 2, 3 in oct. We're going to find the value in decimal. So we're going to do 1 times 64 plus 2 times 8 plus 3. That's going to give you 1, 2, 3 in oct is 83 in decimal. So to show you that the numbering system in hex is a better representation of the binary numbers than decimal is, we're going to convert from binary numbers to hex numbers. So in this case, each hex digit takes the place of 4 bits. So all you have to do is convert the first number and then convert the second number. So here we have a binary number, but instead of putting the place values all the way out to 128, we're going to split the binary in half, translate the first half, then translate the second half. So for the digit on the left, the 0011, we have a 1 in the 2's place and a 1 in the 1's place, so 2 plus 1 is 3. On the right side, we have an 8 plus a 2 plus a 1, so 8, 9, 10, 11, or in this case, B. So our hex number for that particular binary number is 3B. So we're going to convert the number ED. Yes, it's a hex number even though it's ED. ED is going to be converted into binary. So first we're going to split the number into 2 digits and then convert each of those digits separately. We know that E is 14, and we're going to convert 14 to binary. So we're going to put a 1 in the 8's place because 14 is greater than 8. And we're going to subtract out 8 from 14. We're left with 6. 6 is greater than 4, so we add another 1 onto the number in the number's place, and we're left with 2 left over. That means since 2 is equal to 2, we're going to put a 1 there in the 2's place, and then we're left with 0, so there's just going to be a 0 in the 1's place. All right, now for the D side. D is 13. 13 is greater than 8, so we're going to put a 1 there. Subtract out our 8, we're left with 5. Well, 5 is greater than 4, so we're going to put a 1 there and subtract out the 4. We're left with 1. So that means a 0 in the 2's place and a 1 in the 1's place. So our binary number 11101101 is equal to ED in hex. Okay, we can convert numbers back and forth from binary to decimal and decimal to binary, but sometimes you don't want to convert the numbers. I'm going to show you how to add binary numbers without having to convert them. So here's our math problem. We're going to have 00110101 plus 10110110. Okay, we're going to start adding the numbers on the right-hand side, just like you were taught in the 2nd grade for regular numbers. Okay, so here we got 1 plus 0 is 1. And 0 plus 1 is 1. So far, so easy. Okay, now it gets a little trickier. Here we have 1 plus 1. Well, that's 2, but there's no 2 in binary numbers. 2 in binary is 1, 0. So we're going to carry the 1 and put a 0 down below. So now in the next column, we have 1 plus 0 plus 0. Easy, that's just 1. I'm going to bring a 1 down. Now we're going to add 1 plus 1. Well, that's 1 plus 1 is 1, 0. We're going to carry the 1 and put a 0 down below. Now we have a tricky one. We have 1 plus 1 plus 1. Okay, that's 3, but there is no 3. And 2 is 1, 0, so 3 is 1, 1. I'm going to carry the 1 and put a 1 down below. So the next column, we have 1 plus 0 plus 0. That's just 1. And 0 plus 1 is 1, so this is our answer. And it should match up pretty well. If you can convert the top number into decimal, you get 1 plus 4 plus 32 is 53. And then the bottom number, we have 2 plus 4 plus 16 plus 32 is 1 plus 128 is 182. If you add those numbers together, you get 235. So the answer in binary converted into decimal should be 235. Let's check it out. 128 plus 64 plus 32 plus 8 plus 2 plus 1. That equals 235. So we've done our math problem correctly. Okay, we've converted from binary to decimal and back again. We've converted from hex to decimal and back again, added in binary numbers, and now it is time for the joke of the day. Joke of the day, joke of the day, ha ha ha, hey hey hey. Why do computer scientists get Halloween and Christmas mixed up? I don't know, Mrs. Murphy. Why do computer scientists get Halloween and Christmas mixed up? Because Oct 31 is decimal 25. Ha 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 ha. All right, well, good luck with the homework assignment. Should be pretty binary-ific.